Acids, bases, and salts. On page 146, we discuss the properties of acids. We learn that they taste sour. That probably doesn't come as a huge surprise, but you might wonder why acids taste sour. It's because human beings for many generations have had a sensor on their tongue that detects the presence of positively charged ions like hydrogen. Acids, when dissolved in solutions, are electrolytes. That means they're able to conduct electric charge. You may have seen a version of this experiment where nails made from two different metals, perhaps one copper and one nail, are placed in a fruit like a lemon. The nails differ in their ability to move electrons around, and this causes a circuit to form from one side of the lemon to the other, and the moving electric charges in that circuit are sufficient to do a little work, like perhaps causing a little light bulb to glow. So acids are sour, acids are electrolytes, and acids will cause an indicator to change color. Here you see flask going from clear to pale pink to darker pink to red. What's going on? Well, an indicator is just a molecule that's dissolved in solution that actually has a certain shape. As you can see from the animation, that shape is capable of changing in solution. That's because the bonds of the molecule are free to rotate. And there are parts of the molecule which either have positive or negative charge, which means if you change the environment that the molecule is dissolved in by adding or subtracting positive or negative charge, the molecule may rotate and the process change shape. And by changing shape, it reflects light differently. Larger molecules tend to reflect larger light waves, colors on the warm end of the spectrum, yellow, orange, red. Smaller molecules tend to reflect smaller light waves on the cooler part of the spectrum, green, blue, and purple. And so altering the shapes by changing the charge in that environment will cause the molecule to reflect light differently, and we experience that as a change in color. And this is an actual molecule you see in this animation, phenolphthalein, that we will use in one of the experiments in class. Now, if acids taste sour, what do bases taste like? Well, just like acids, bases have a taste which is bitter. And just like acids, that bitter flavor is based upon a particular sensor on the tongue. And again, natural selection has caused human populations to acquire the ability not only to detect positive charge, as in the case of acids, but in negative charge, as in the case of bases. Like sourness and saltiness, a specific sensation of taste, it's associated with a particular kind of bug on the tongue. Now, bases feel slippery, like soap. And I've often cautioned students during lab, if you feel a slippery or soapy sensation on anywhere in your skin, you should probably wash it right away. It's not necessarily life-threatening, but we don't want to lose some skin. It's just a good safety precaution to do that because the solution to pollution is dilution. Add a little water. Now, bases taste bitter. They feel slippery like soap. And just like acids, they are electrolytes, and aqueous solution will cause indicators to change color. Here you see a cartoony kind of diagram of an experiment that we'll do in this unit, which is called a titration. More on that later. Now, why is it that we have charged molecules at all when they're dissolved in water? Well, let's remember that water molecules themselves are highly polar. That is, opposite sides of water molecules differ in charge. In this illustration, the side dominated by the two hydrogens shown in blue with plus signs tends to be slightly positive, whereas the side dominated by the sole oxygen, which is -2, shown in red, tends to be slightly negative. From a distance, the water molecule is neutral because the charges cancel out, but if you're on the hydrogen side, you might measure a slight positive charge, and on the oxygen side, you might measure a slight negative charge. These opposite charges cause water molecules to have a weak attraction for each other in solution, which is sometimes called hydrogen bonding. It's not actually a chemical bond because no electrons are shared or transferred, but it is a weak attraction because the positive side of one water molecule will be attracted to the negative side of another. And this is why water tends to bead up on a surface. Now, these hydrogen bonds themselves aren't very strong. Again, they're not truly chemical bonds. They're individually weak. And because they are weak, random collisions between water molecules can supply enough energy to transfer a hydrogen ion from one water to the other. This is a process called autoionization, or in your textbook, self-ionization. It's the same thing. Here in this illustration, you see a double arrow. It's a reversible reaction where two water molecules are the reactants and the products are H3O plus and OH minus. What's going on? Well, in this case, the particles that are produced are charged. The hydronium ion, H3O plus, is a water that has stolen the hydrogen from another water. And the hydroxide, OH minus, that's the water that lost one of its hydrogens. One tends to have a charge of +1, one tends to have a charge of -1. At this moment, the idea that water molecules might be falling apart might be a little disturbing. But don't worry. In the first place, such collisions are actually rare. At any given moment, in pure water, only about 1 in 10 million water molecules will undergo this reaction, which is called the dissociation of water. So it's not very common. Also, it is a reversible reaction. And remember, the odds against it going one direction are 10 million to 1 against. That means the um, odds of it being reversed and going back and reforming water is extremely high, 10 million to 1 in favor. So in neutral water, these separate charges would be canceled out anyway, but you don't have to worry about them staying in this condition because it would be quickly reversed. And again, whether it's happening or not, in which direction, the overall charge of the water at all times it would remain neutral, unless there's something in there besides water. If any substance dissolved in the water upsets the balance between hydronium, H3O plus, and hydroxide, OH minus, we will have a solution that is not neutral, which has a net charge. When this happens, we get acids and bases. Acids can be defined as substances that increase the amount of hydrogen ions, H plus, and therefore decrease hydroxide, OH minus. Bases can be defined as substances that increase the amount of hydroxide, OH minus, and decrease H plus. In the illustration you see, we have a bunch of rectangles of different colors. In the very middle, labeled pH 7, we have a blue rectangle, and this represents the pH of pure water. Now all the colors that are above it, the greens, the yellows, the oranges, and the reds, these are pH 6543210. Those are all acids. And all the colors that we see below the blue rectangle labeled 7, the purples and the pinks, well, that's 8, 9, 10, 11, 12, 13, 14. Those are all bases. This is the pH scale. It's used to determine how acidic or basic a solution is. It goes from 0 to 14. Counting numbers, which makes it convenient and easy to use in everyday purposes. But there's kind of an easy and a hard version of the pH scale. In the easy version, we use the counting numbers, which are small and positive. But these small and positive numbers are actually defined as being equal to the negative logarithm of the concentration of H plus. Whenever we have a symbol or a number in brackets in chemistry, chances are it refers to concentration. And that's the case here, where you see bracket H plus, that means the concentration of H plus. And so we have small positive counting numbers, 0 to 14, but they actually represent negative powers of 10. And so the numbers here in the pH scale are actually tiny little numbers. They are decimals, something less than 0, and often we express them in scientific notation. But in the simplified version, it's really straightforward. If you have a number less than 7, which in this picture means that you're green, yellow, orange, or red, why you have a number less than 7, you are an acid. Whereas if you have a number greater than 7, you're pink or purple below the blue rectangle in the middle. If you have a number greater than 7, you're basic. And if you're exactly pH 7, just like the blue rectangle in the middle of the illustration, while you're neutral. And you'll notice here that water is the standard, just as water is the standard for density, how much stuff and how much space. It's the standard for, storing energy in a sample. It's also the standard of, keeping track of positive and negative charge. It's in the very middle of the pH scale. Notice that while pH is defined as the negative logarithm H plus, as this illustration from our textbook makes clear, it's actually not hydrogen ions which are occurring in solution. Hydrogen ions do not, in fact, occur in solution. Instead, the positive ion, which tends to form in both neutral water and solutions, is hydronium. And you can see that in the first column of this illustration. It's actually a hydronium, H3O plus, that's in brackets, not hydrogen. And you can see that these are all actually negative powers of 10. Whereas with the acids in the first column, the numbers at the top are low and they descend and they become bigger and bigger, but they're only becoming bigger in the sense that they're larger negative powers of 10, which means they're actually becoming smaller. And the next column, which is for the hydroxide, the numbers are going in the opposite direction. And what's interesting about this is that the product of positive charge and negative charge, if we take the concentration of the positive and the concentration of the negative, and we multiply them by each other, we get a constant product, which is 1 times 10 to the negative 14th. That's an interesting and fundamental fact about the pH scale. Now, strong and weak acids, strong and weak bases are characterized by how they actually behave in solution. So a strong acid is one that becomes completely ionized in aqueous solution. Every part of it, as it dissolves, gets broken up into particles of separate charge, ions. So for example, in the reaction where hydrochloric acid is dissolved in water, HCl and H2O, those are the reactants. The products are hydronium and chlorine ions. And in this case, all of the hydrochloric acid, all of the HCl is converted into hydronium and chlorine ions. So hydrochloric acid fits the definition of a strong acid because every bit of it is converted into either positive or negatively charged ions. As shown here. In contrast, weak acids only ionize slightly in aqueous solutions. Little bits of it ionize, but a lot of it doesn't. A lot of it just sits there. And so we say that acids and bases form conjugate pairs based on their relative strength, whether one is strong or whether one is weak. And we can measure the strength of that relationship by a dissociation constant, which basically is just measuring, how much does it dissolve? How much does it ionize in aqueous solution? How much does it not? It turns out every acid or base has a dissociation constant. We sometimes say K sub A for acids and K sub B for bases, but in essence, they are the same thing. They tell you how much the acid or base will actually separate into ions when dissolved in water, and they form acid-base pairs. You'll have a strong acid paired with a weak base. You'll have a weak acid paired with a strong base. Now, what about water? Now, water's a funny thing. It can act like an acid or a base. Remember, just like an acid or base, it can separate into ions. Water is capable of autoionizing or self-ionizing. It does this in a reaction, which again is reversible, called the dissociation of water. Now, when this happens, when neutral water is broken apart, one more water rather becomes positively charged, and the other water becomes a negatively charged ion. But the total amount of positive and negative charges that are going into solutions are the same. And the relative concentration of the positive negative charge is always about the same. It's 1 in 10 million. We say 1 times 10 to the negative 7th. If you wrote it as a decimal, it's 0.00000001. It's a small number. It's not truly a negative number. It's just a negative power of 10. But it's a small number. But that small number is the same both for positively charged hydronium and negatively charged hydroxide. So if we try to calculate the relationship between the two of them in neutral water, we always end up with the same number. So this is why water has a constant of its own. Water could act as an acid, it could act as a base, but at the end of the day, water has both positive and negative charges in it. But the product of the positive and negative charges in neutral water is always going to be 1 times 10 to the negative 7th times 1 times 10 to the negative 7th. And the rule for multiplying exponents is that we add the sign. And so that constant, your textbook calls it the ion product constant for water, K sub W. That number is 1 e to the negative 14, or 1 times 10 to the negative 14. It's a constant. And that comes in handy when we're trying to figure out the constants of other substances like acids or bases. Now again, every acid or base has its own dissociation constant. We have here constant shown for an acid, hydrochloric acid, and for a base, sodium hydroxide. And one's very small and one's very large. But again, they're just telling you how much of the acid or base will separate into ions when dissolved in water. Now, the larger the constant, the more the acid forms ions and the stronger the acid. And we can use the strength of that constant to predict the rate at which acids and bases react. The larger the constant, the stronger the acid, the faster that they will tend to react with one another. These constants can also be used to predict the point of equilibrium. We say K sub EQ instead of acid dissociation constant or base dissociation constant. We're talking about the point where everything's going to be balanced again. And what's being balanced, why it's the products in the reaction and the reactants in a reaction. So here we have actually a reaction which is reversible. Hydrochloric acid and water will react. And again, hydrochloric acid is a strong acid, and so we expect that most of it's going to be converted into ions, hydronium and chloride. And we can represent mathematically what that equilibrium point is by using this following expression. We say K sub EQ equals the concentration of hydronium, which is the positively charged product, times the concentration of chloride, the chloride ion, which is the negatively charged product. Those are the products, right? They're after the arrow. And we're going to divide them by the product of the original concentration of hydrochloric acid and the original concentration of water. Okay, so got it? We got concentration of hydronium times concentration of chloride on the top. We've got concentration of hydrochloric acid and concentration of water, the reactants, on the bottom. Let's now use the concentration of hydronium, H3O plus, in a sample of hydrochloric acid. Suppose it's 0.000035. So we're using a decimal to express that concentration. It's one of the products, it's on the top. While the concentration of the chloride ion, Cl minus, it's 3.72 times 10 to the negative fourth. So for that product, the chloride ion, we're using scientific notation. But whether we're using a decimal or scientific notation, it's just ways to express really small numbers between 0 and 1. Okay, so if we've got concentration of one times concentration of the other, well, we're just going to multiply them. And the top form of this equation is thus equal to the product of those two numbers. And if we do the math, it's a tiny number, 1.3 times 10 to the negative eighth. Now, what about the bottom? How do we figure that out? Well, the stuff on the bottom, these are the reactants, hydrochloric acid and water. And strong acids like hydrochloric acid are just treated as one. And of course, we just learned that the dissociation constant of water is 1 times 10 to the negative 14th. So we're going to take the product of the top, which we already learned is some tiny number times 10 to the negative 8th, and we're going to divide it by 10 to the negative 14th, which is an even smaller number. And so we end up with a pretty large number. And so the equilibrium point K sub EQ in this case happens to be a large number, 1,302,000. And all that means is that when the concentration of the products is about 1,302,000 times greater than the original concentration of the reactants, well, then we're going to be at a happy place and the relative amounts will all remain constant from that point on. That's all we're saying. Now, for strong acids like hydrochloric acid or nitric acid, you have to include a term for water as the reactant. But as you see, we just use its dissociation constant. But if we got weak acids, well, then we can treat the water as a constant. And so we can actually make that equation even simpler. When we're talking about weak acids, the general form for the acid dissociation constant is we're going to have the concentration of hydronium multiplied by the concentration of some negatively charged ion. In the last example, it was chloride. It could be anything that's negatively charged. And then we're going to divide that by the original concentration of the acid. So hydronium, concentration of hydronium times concentration of anion divided by the concentration of the original acid, and we can ignore water. We'll just treat it as a constant. Now, while the equation to find the dissociation constant of these various substances is useful for predicting what will happen when a given acid or base is dissolved, in practice, the constant must be confirmed experimentally, often by doing experiments. Specifically, we're going to be doing titrations. Titrations is a procedure for determining the concentration of an acid or base, which is unknown. And how do we do it? We add an acid or base of a known concentration. We will start at a certain point where they are not the same. There'll be an indicator in the flask or the beaker that's receiving drops of the oppositely charged solution, but they initially won't be balanced. We'll get this equivalence point from the mole ratio, and the goal is that we'll reach the point where all of the acid or the base has been neutralized by all the base or acid which we add. When this happens, we will see a change in an indicator that's meant to show a change right around the equivalence point, right where the point where positive charge is replaced by negative charge or vice versa. And we get characteristic curves that are kind of like an S that's very straight in the middle. Different indicators give us different curves, but the basic shape of the curve is the same. Eventually, we'll get to the point where the indicator changes color. We call that the endpoint. And if our technique is good, ideally, the endpoint, the point where it actually changes color, should match the equivalence point. Some skill is required in doing a titration. Now, in a titration, we can use it to neutralize a substance of unknown concentration. And the classic is the pairing is that we would have hydrochloric acid as a strong acid, and we would have sodium hydroxide as a strong base. And this will be a neutralization reaction where the product is simply water. Now, titrations demonstrate patterns based on whether we have strong or weak acids or strong or weak bases. Let's talk about the strong ones. If we're going to talk about strong acids, there are a total of 6 of them. They have constants K sub A's, which are greater than 1. So here we have hydrogen iodide, or hydroiodic acid, hydrobromic acid, hydrochlorous acid, hydrochloric acid, sulfuric acid, and nitric acid. And you can see that they all have dissociation constants, which are greater than 1, all the way from nitric acid, which is basically 2, and all the way up to hydroiodic acid, which is 1 times 10 to the 11th power. Now, for the strong acids, we also have strong bases. And these are also good to memorize. We have a total of 8 strong bases, which have constants greater than 1. Lithium hydroxide, strontium hydroxide, barium hydroxide, potassium hydroxide, cesium hydroxide, sodium hydroxide, calcium hydroxide, and rubidium hydroxide. You may notice a theme here, right? They're all hydroxides, right? And they're all actually combining with metals from either group 1 or group 2. So if we have a strong acid and a strong base, the pattern of a titration is that we're going to have a neutralization reaction which leads to the production of water. But if we have weak acids and weak bases involved, they will only partly ionize the solution. Remember, they don't completely go. And so they participate in reversible reactions with their strong counterparts. And so in these reactions, the products will be conjugate pairs, and the conjugate pair will typically include water. So in the example of a weak acid and a strong base, you'll have your conjugate acid interacting with something that donates hydroxide, and your products are water and a conjugate base. Whereas with a strong acid and a weak base, you'll have a source of hydronium, something upsetting the balance in a conjugate base, and the products of that will be water and a conjugate acid. So notice that in one reaction, water is going to act like an acid, and the other reaction, water is going to act like a base. Again, this is the phenomenon where water autoionizes or self-ionizes. Water is always involved in the neutralization of acids and bases, regardless of its strength, because water is amphoteric, which is just a fancy word meaning it can act as either an acid or base in a solution. And again, notice that in the top reaction, water acts like a base, and it produces the conjugate acid hydronium. And then the reaction underneath, water acts like an acid, and it produces the conjugate base hydroxide. Autoionization. And here, this isn't actually meant to represent a chemical reaction, but in a way it does, because this is the reaction of autoionization. And even in autoionization, water serves as both an acid and a base. One, water will give up a hydrogen and it will produce a conjugate base, hydroxide. The other, water will gain a hydrogen and it will produce a conjugate acid, hydronium. So one water acts like an acid, the other one acts like a base. As mentioned before, water molecules spontaneously dissociate into these two pairs, and it turns out hydronium is a conjugate acid and hydroxide is a conjugate base. When we do the math, remember the concentration of both hydronium and hydroxide is going to end up being 10 to the negative 7th, which means pH and pOH for neutral water will be 7 for both of them. And again, this is just another way of stating what we've already mentioned, which is the product of the concentration that ions produce in the reaction is a constant. Okay, so this may seem a little bit strange to keep going back and forth about this and saying the same thing over and over again and looking at autoionization from different points of view and emphasizing 1 times 10 to the negative 14th from different points of view. But the fact of the matter is we're dealing with something that's a little tricky. We're dealing with positive and negative electrical charge. And the fact is, in nature, chemical systems are rarely neutral. Instead, there is a tug of war between competing forces in almost all situations, which leads most substances or solutions in a bunch of different possible conditions in order to deal with their excess electrical charge. As a consequence, acids and bases are typically defined in a number of different ways. This is potentially confusing, but just keep in mind that one definition can work better in one situation than another. The reason we have more than one definition is because there are different situations. So one way to define acids and bases is the Arrhenius definition. The Arrhenius definition is talking all about hydrogen ions. Substances that release hydrogen ions, H+, when dissolved in water. Now, obviously, if you're trying to measure hydronium, which is what actually founds the solution, Arrhenius is a little problematic. Bases are the opposite. Bases are substances that release hydroxide ions when dissolved in water. All right. So the Arrhenius definition is about what ion is going to be released when it's dissolved in water. So for example, since sodium hydroxide produces the hydroxide ion when it's dissolved in water, the Arrhenius definition classifies sodium hydroxide as a base. Now, again, we want to remind you that the hydrogen ions, H+, if they associate with water molecules, they form hydronium ions. We don't find hydrogen ions just floating in solution because they will associate with water molecules when they can. Now we have the Bronsted-Lowry definition. This is all about whether you give up or receive the hydrogen ion. So an acid is a substance that's said to donate H+, and a base is a substance that accepts H+. The Bronsted-Lowry definition is just interested in which direction the hydrogen ions are going. It doesn't say anything about hydroxide. And so amphoteric substances like water, they can act either as a Bronsted-Lowry acid or as a Bronsted-Lowry base, as we learned when we considered water's ionization in detail. So an example of the Bronsted-Lowry definition is an equation we've used before where hydrochloric acid reacts with water to form hydronium and chloride ions. So hydrochloric acid is the original acid, a reactant. Water is the other reactant, and so it serves as an original base. Hydronium is the product, and since it has an overall positive charge, it serves as it is a conjugate acid. And then chloride is also a product, and it's the conjugate base. Again, so you see how hydrochloric acid donates a hydrogen, producing the conjugate base chloride, and how base accepts a hydrogen and becomes a conjugate acid hydronium. So again, the Arrhenius definition has to do with whether a substance is giving off positive or negative charge. The Bronsted-Lowry is about whether something is donating or receiving a hydrogen ion. And the Lewis definition, well, it's all about whether you're giving or receiving an electron, which is why this slide is green. Lewis definitions defines an acid as a substance that accepts a lone pair of electrons, whereas a base is a substance that donates a lone pair of electrons. When talking about the Lewis definitions, it's helpful to be able to talk about them in terms of whether you accept or receive the lone pair. So your analysis should look for the question of what chemical bond had to be broken or what chemical bond had to be formed that involved a lone pair. Now, the Lewis definition is more general than all the other definitions, so it turns out that all Bronsted-Lowry acids and bases are also Lewis acids and bases, which is convenient. And a difference between them can be summarized in this table. Again, as you can see, the Arrhenius definition involves both H plus and OH minus, but it does not involve electrons. Bronsted-Lowry is only about whether you get or receive a proton, H plus. And the Lewis definition doesn't have anything to do necessarily with either of the charged particles donated or received. Instead, it's all about whether you're getting or giving the lone pair of electrons. Lewis acids are helpful in distinguishing between two broad classes of reactions, those that transfer electrons and those that don't. In oxidation reduction reactions, electrons are exchanged, while in neutralization reactions between acids and bases, protons are exchanged, but electrons are not. Now, when talking about neutralization reactions, they lead to the formation of ionic compounds, which are often called salt. We all say sodium chloride is salt, table salt, but that's a particular kind of salt, and it turns out that in chemistry, salt is a general term that really is used to talk about almost any compound that's formed by a neutralization reaction between an acid and a base. Salts, of course, occur in solution, and they can come out of solution. As the solutions evaporate, we can see crystals of salt appear from where there was once a solution. Here, this is a picture taken at the Dead Sea, which is one of several bodies of water on this earth, which are super salty. In fact, this object in front of you is actually a tree that fell over near the edge of the salt sea, and over time what's happened is that salt crystals have formed on the dead crust of the tree. And you can actually see close to the crust that there are things that look like waves, but they're actually not. They are crystalline shapes where waves once were. So salts are formed when ionic compounds like sodium chloride dissolve in water. Again, they are the product of a neutralization reaction between either an acid or a base. And salts can produce either acidic or basic solutions, depending on whether they have excess positive or negative ions. So there are some salts, if you dissolve them, you produce a solution that's an acid. There's other salts, when you dissolve them, you produce a solution that's a base. Salts can be used to create what are called buffer solutions, which are very useful in chemistry. These are solutions which do not change pH quickly due to the presence of extra ions in the solution that will bond to either H plus or OH minus. They consist either of a weak acid or a weak base with a corresponding salt. For example, if you add the acid hydrochloric acid to a buffered solution containing a base, sodium ions can be used to replace the H plus, which leads to the salt sodium chloride. And this slows the rate at which the solution's pH would change. You'll notice in the picture we have several containers, plastic containers, and they're actually labeled buffer solutions, and they have different pHs shown. For example, the big jug closest to us says pH buffer 7, whereas the blue cylinder says pH buffer 10. So different buffer solutions are made at different pHs for the purpose of doing chemical reactions at a particular pH. So chemists often add buffer solutions with a specific pH to control the rate of different reactions, and this allows them to get a higher yield, to get more product, and often it allows you to get a safer yield because not as much energy has to be pulled in or taken out of in the desired reaction. So acids react with bases in solution in neutralization reactions whose products include water and a salt. Here you have a schematic. HA stands for acid and BOH stands for base. And you can see that the A in the acid and the B in the base combine AB to form the salt, whereas the H and the OH in the two reactants combine to form water. It's a kind of double displacement reaction. Here's a specific example that applies it. When the reaction of hydrochloric acid and sodium hydroxide, the sodium and the chlorine come together to form sodium chloride, a kind of salt, and the H and OH combine to form water. Acids will react with all metals that appear above hydrogen electromotive series, and in the process, they will engage in reactions that release hydrogen gas in single replacement reactions. So one example here is magnesium reacts with two hydrochloric acids, and we produce magnesium chloride and, oh, by the way, hydrogen gas. Here, each of the two hydrochloric acids donates one proton, H plus, to form a single H2 molecule, and it also donates one chloride ion to make the ionic compound magnesium chloride. Acids will not readily react with any metal that lies below hydrogen in that series, in particular copper, mercury, silver, and gold. And so that's one of the reasons why these things are considered to be precious metals, because unlike other metals, you put an acid on them, they won't fizz and bubble and corrode and break down and fall away. They resist corrosion. Meanwhile, bases in metal cations like sodium plus or calcium double plus, they'll enter into double displacement reactions. A good example here is we have aluminum nitrate reacting with 3 moles of sodium hydroxide. The aluminum gains 3 hydroxide groups, and we end up with 3 moles of sodium nitrate, right? The nitrate and hydroxide groups have switched places, double displacement reactions, and we get characteristic colors from these metal cations reacting with bases.